Alright, this is Mr. Griffith again, and in our last video we were discussing some properties of addition and subtraction of whole numbers, and we got all the way up to the identity property. Now, we had started out by giving something of a visual description of a set, and you can see here's the universal set, and here are a couple of disjoint sets. We'll call them A and B, and let's put in another disjoint set from that, which we will call C. And so we're going to explore another property. We have already, as I said, explored the identity property. The identity property of whole numbers essentially says that any whole number plus 0 is that same whole number. All right. We talked about the commutative property. The commutative property said that it did not matter what order we added our whole numbers in. So we did the identity property, we did the commutative property. Let's see. So identity, commutative. We did the closure property. That's right, the closure property, the one that people most easily forget. Okay, which says that the addition of any two whole numbers is a whole number. So the sum of A plus B is a unique whole number. So today we're going to do the associative property, and then we're going to take a look at some other things regarding addition and subtraction. And so with the associative property, you can see here that A union B, okay, if I take A union B and put those sets together, all right, that'll create one larger set, and then I can put it together with C. But that's going to give me the same result as if I took B and C here, put them together first, all right, took the union of them, and then enclosed A as well. So A union B union C. This parenthesis indicating that B and C were put together as a group before being combined with A. Well, then you can see that this and this are the same. Well, again, remember we are working with disjoint sets. All right, we are working with disjoint sets. So we are able to say the number in A union B plus the number in C, okay, set C, is equal to the number in A plus the number in B union C. And so then this is the number in A plus the number in B plus the number in C is the number in A plus the number in B plus the number in C. Okay? Or as we know, if we say little a is the number in A and little b is the number in B, little c is the number in C, we get this result. Okay. And this essentially is the associative property of addition, where you can see that it does not matter what you group first. Okay. So how does this associative property of addition work? Okay. Well, suppose I had 3 plus 4 plus 6. I could indeed do 3 plus 4 first and get 7. 7 plus 6 is 13. Or I could recognize that 4 and 6 make up a nice number, 10, and 3 plus 10 is 13. And either way, I will get the same result. So these are basically the 4 properties that we have with addition. And A plus B plus C is A plus C, right there. Okay. So these are 4 basic properties of addition. You can see that we derived them all from set ideas regarding disjoint sets. Okay. Now, remember that we had talked about the idea of comparing sets using a one-to-one correspondence. And so let's suppose that I have set A as being A, B, C, and D, and set B as being A, C, and E. Okay, so you can see right there that these two sets are, well, different. I'll tell you what, let's make them disjoint so they don't have anything in common. E, F, and G. All right, so these are 2 disjoint sets. Okay, and now if you take a look here, if I put a one-to-one correspondence in here, okay, I'm frustrated because A is not equivalent to B. A does not have the same number of elements as B. In fact, there is some part of the set left over. Okay, I could take a look at this idea here. There is some number of elements in set A which cannot be made put in this correspondence. So we're going to talk about this idea of greater than in this way. We're going to say that let the number in A be equal to A and the number in B be equal to B. Then, okay, A is greater than B if there is some whole number greater than 1, okay, we'll call this whole number K, greater than 1, such that the number in B plus K, okay, is equal to the number in A. Okay, that is, or the number in B, so that would just be B plus K is equal to A. So there, the number in B plus 1 here is the number in A. Now, this idea of greater than, you can also see it'd be easy enough to write less than. We could say B is less than A if there is some whole number K greater than 1 such that B plus K, K is equal to A, and same sort of thing. Okay. So, we can see this though from a set theoretic potential here. B is equivalent equivalent to a subset. In fact, not just a subset, a proper subset of A. So when I take a look at this, since I see that set B is equivalent to some proper subset of A, I know that B is less than A. Now, this is going to give us an idea of subtraction. Okay? And what I'd like you to see is that if I want to compare these two sets, there's not just the idea of whether it's greater than or less than, but greater than by how much, or less than by how much. And so you can see here that the number in B plus K is equal to the number in set A. This K being the number of elements that A has that would not, that are greater than B. So I can say from this, okay, essentially B plus K is equal to A. I can make this statement that A minus B is equal to K, all right? And again, K tells me how much greater than the number in set B is the number in set A. Similarly, I could make this statement. I could say A minus K is equal to B. Now, generally speaking, I can define subtraction by addition. So let's talk about two whole numbers, A minus B, A and B. And so if I talk about A minus B, this part's also called the minuend, and this part is called the subtrahend, and this part right here is called the difference. Okay, and I can say that A minus B is equal to C if C is a whole number. Now remember, we're dealing with subtraction of whole numbers. A number such that B plus C is equal to A. Now, this definition of subtraction means that subtraction is the opposite or inverse operation of addition. So, subtraction is the inverse operation of addition. Now, how else might I take a look at this? Well, when we are dealing with these kind of numbers, we can express these kind of numbers to children on a number line. Now, one thing you have to be very, very careful of is to remember that when you're dealing with number line ideas for children at this level, and you're dealing with whole numbers, of course, starting at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we can keep going in that direction. Okay? The children at this point are not going to see this as being, we'll say, 3.5. All right? They're just going to see these as the values. All right? Now, we're setting them up to be able to use this tool in a larger context. So eventually they'll be able to see 3.5. But at this point, they are working with whole numbers. So to them, at this point, these other ideas don't exist. Okay, remember, we're talking about sets, and the universal set in this case is the set of whole numbers. All right, so let's just talk about what 8 looks like. 8 looks like this. 8 is an arrow that is moving in that direction. Okay, so if I wanted to make up 8 by addition, I could take a 3 part, and then I could take this 5 part. Now this 5 part can move, okay? So I can move this 5 part right down here, okay? And so here's this 5 part. I'm adding the 5 to the 3. You see this 5? Okay. And there's the 3, and you can see 3 plus 5 is 8. Okay. Well then, if I want to talk about subtraction, subtraction is the inverse operation of addition. So instead of going to the right, I would go to the left. And so you can see here that on the number line idea, here's 8, okay? And I have arrived at, I have 8. And I'm going to take away 5, so I'm going to take away 5. And so here's the 5 that I am taking away. I am undoing that 5 out of those 8, okay? And you can see, by the way, that that is 3. So this is a number line illustration of 8 minus 5 is equal to 3. Now, we could look at subtraction also as a in something of another way. Instead of this idea of taking away, I can look at 8 minus 5 as a question, all right? How many should I add to 5 to get 8? Okay. So here, essentially, this could be my goal, and this should be what I've got already. And what I want is to know how many more I need. Now you can see this. This is an important concept, because we have the idea that, say, Billy needs $5 to pay for a toy. He has $3. How much more does he need? Well, that would be a 5 minus 3 is 2 problem, isn't it? Okay. And so, in this case, someone needs 8, and they have 5. How many more do they need? So, if I already have 5, here's where I am. Okay. This is where I want to be. And this is what I need. This is what I have, and this is what I need. And you can see that this is a 1, 2, 3 line. So there we are looking at subtraction in a couple of different ways. What you have and what you need. Or what you have and what you're taking away. Now, these two ideas promote two different kinds of ways to look at subtraction on an algorithmic scale. So we're going to be learning later on in another chapter on strategies for doing some of this work. But I'll give you a little hint first, all right? So we know that if we have, let's say, 53 minus, let's say, 21. We can deal with that as a takeaway idea, 53 minus 21. And we can say, well, if I take 1 from 3, I've got 2. And if I take 2 tenths from 5 tenths, I've got 3 tenths. And so my result is 32. Or I could start it off like this. 21 plus something is 53. And you see, I know that if I have 1 1 and I need 3 1s, I'm going to have to add 2 1s. And if I have 2 10s and I need 5 10s altogether, I've got to add 3 more 10s. Can you see that either way the subtraction has been accomplished? But we've looked at it from two perspectives. This is the idea of take away, okay? And this is the idea of what more do I need? They are two different kinds of perspectives, but each of them very valuable.